back to Lecture 1, Organic Contaminants. This is the fourth section on remediation concepts. Let's look at the technologies we'll be discussing in this course and see which ones apply to the source and which ones apply better to the plume. Remember, the source has a high amount of relatively immobile mass, whereas the plume has a low amount of mass spread over a large area and it's quite mobile. Monitored natural attenuation, which we'll discuss shortly, really doesn't do much for the source. It's normally applied in the plume, but it in fact controls both. Pump and treat doesn't really get rid of much of the source mass, but it does a good job on the plume. Sparging, adding oxygen to the system or air to the system, again works reasonably well in the source where the mass is concentrated, but the large area of the plume discourages the use of sparging there. In situ bioremediation has difficulty with the large mass in the source, but seems to work a little bit better in the plume. In situ chemical oxidation, again, likes to be applied where there's a large amount of mass, and it can be applied in plumes, but hasn't been applied there very often. Permeable reactive barriers, which we'll again discuss later, aren't really used in the source. They're used to cut off the plume, so they're a plume treatment technology. Solvent or surfactant flushing is really reserved for the source, where we have NAPL, not in the plume. Thermal technologies, again, are useful where there's a high mass, but not terribly useful where there's not much mass. Here's an interesting reference that discusses the application of remedial technologies in the early 2000s. The diagram on the left indicates the ownership of sites in the US, and overall there's a little bit over $200 billion in remediation anticipated. On the right we can see the sorts of sites that people are dealing with. Underground storage tanks make up quite a few of them. State and private facilities, including probably many DNAPL sites, make up the bulk of the problems. So, lots of money being spent, lots of contaminated sites. Well, before we get very far in remediation, it's useful to have an objective. So what would be reasonable objectives? Well, one objective might be to remove all the contamination. A different objective may be to reduce the risk of exposure to contamination for humans or ecosystems. Some suggestions we might have. Certainly objectives have moved past the time where we simply proposed reducing concentrations in plumes to certain levels. We have to be a bit more holistic. For example, if the aquifer was a drinking water aquifer, it might be reasonable, the public may expect us, to return the aquifer to a drinking water condition. That would mean not only treating the parameters of concern, but also ensuring that aesthetic and other parameters were within the drinking water objectives. Over time, we've realized we have limited success in cleaning up sites, especially if our objective is to remove all the contaminants. And I think remediation objectives are becoming a little bit more realistic. The difficulty, of course, is dealing with the public expectation. The public quite often expects much more than we can produce, and that's an ongoing problem. For example, if we decided our objective was to remove everything, we'd have to remove all the contaminant in all these different phases: vapor phases, dissolved phase, residual NAPL, free phase NAPL, sorbed contaminants. That would be quite an undertaking. It's useful to look at remediation, as we've done, in terms of application to sources and applications to plumes. Remember, the source has a lot of mass that's fairly immobile, whereas the plume has less mass, but it's quite mobile. One technology that was applied from the earliest days was pump and treat. The idea is to extract contaminated groundwater, treat it, and discharge it. Typical approach was to put in a number of pumping wells and to pump. Remember that the contaminants are distributed among different phases. They're residual NAPL, freeze phase NAPL, sorbed, dissolved, vapor phase. And so that's what we're trying to remove, all of those. Typically, mass removal was very impressive initially, but quickly dropped off, and less mass was recovered over time. The view was there was probably a direct processes dominated early times and indirect processes dominated later times. What do we mean by these? Well, direct action would be removing the dissolved contaminants by pumping out the contaminated water. Removing free-phase NAPL would be a direct action. Indirect actions, which dominate later time, include the process whereby the NAPL residuals that are left behind from the direct stage dissolve in water and are removed in the water. That dissolution is probably a slow process. Sorbed contaminants similarly come back into the water, and that's a slow process. Vapor phase may also be removed, or it may come back into the water and be removed that way. The general observation was that the ultimate removal was far less than our goal. Another technology that was applied early on and is still applied in jurisdictions like Ontario is digging out the contaminants and taking them to some place where they're less hazardous. Dig and dump. Typically applied at petroleum hydrocarbon sites because of the shallow nature of the contamination. In this case, we would simply dig up and remove the underground storage tank, the residuals, and the free phase if we could get it. So we're really doing a source zone remediation. What we leave behind, of course, is typically a little bit of residual that we didn't get, often below the water table, and the dissolved plume. But the hope has been that by removing the source, the dissolved plume will fade away by natural attenuation. Well, what happens if a building had been there? We couldn't dig. That spurred the development of alternate technologies to deal with those sources. We'll discuss some of those in the course. In any event, trying to clean up everything or to dig and dump DNAPL sites is a real challenge. This would entail a lot of digging since the DNAPL sometimes penetrates down to 100 meters. More recently, risk management has become the favorite approach. The idea is to somehow reduce the risk of exposure to some acceptable limit. Typically, this is done by controlling the plume or focusing any remediation on the plume. Two approaches we can think of are one is to treat the plume and the other one is to simply stop the contaminants from migrating. Treating it might involve pump and treat, but we're going to pump a long time. In situ chemical oxidation, bioremediation, air sparging can also be used. But in this case, our objective need not be to remove all the contaminant. It's simply to allow the natural processes to take over and adequately treat the system. The other approach, besides treat it, is to stop it. We can do that with a physical or a treatment barrier. Physical barrier is pump and treat. Good extraction wells are a good way to stop the plume moving forward. Treatment barriers, we'll talk about permeable or active barriers where the water is allowed to carry on, but the contaminants are removed. So, in summary, we've indicated that defining the objectives and making them reasonable is a key issue. Remember that complete remediation is usually not possible, so we'll have to have a different objective. Risk management is a current approach. It involves none or partial remediation and or containment. And we'll discuss these as we move ahead. Next lecture, we'll start discussing partitioning between phases, and that's important for remediation because in many remedial technologies, the approach is to transfer the contaminants from one phase to another to promote treatment. Till then, thank you.